right, so today I'm going to talk about how we do vision-based structure for motion, stereo vision for the autonomous nanosatellite swarming project. Mostly I'm going to talk about the project and very little about the stereo vision aspect, but the project is really, really interesting. This is actually a project that's been going on for, I don't know, 5-6 years at this point. It's had many members over the years, but including Tommaso at one point.
That's true.
Yeah, and so, but over the last 2 years, it's been primarily me and my co-author, Nathan Stacy, who just defended with his PhD. Okay, so quick overview of the agenda. I'm going to go over the objectives of ANTS, talk about the structure of it, and then I'm going to go into each of the various components that have been developed for this project, a quick case study, and then how we generalize the target from the asteroid, which is in the case study, to spacecraft or other targets that we're interested in. Okay, so there are a lot of targets that we're interested in characterizing. Generally, when we don't have things like a shape model or anything like that, these can be non-cooperative spacecraft if there is something that we need to perform maintenance on or something. Comets and asteroids, we generally do not have a highly detailed shape for them, or we don't know their gravity, we don't know the rotational motion, things like that. Other interesting aspects that we would like to characterize within space are orbital debris, which is super hot right now, as well as rocket stages or refueling. You know, if you want to reuse a rocket stage and up in space, if you had something like a CAD model before, it may not actually be what it is up there because of deformation and things like that happen, and you need to recover those characteristics. So what are these actual characteristics? Well, obviously a shape model that you can see here, but the main aspect is usually translational or rotational motion. You'll get something like a 3D polygon model, or you can have a spherical harmonic model that you can get from any sort of visual or LiDAR, things like that. And then there are gravity coefficients. If it's something large enough to have its own gravity, like a comet or an asteroid. But the thing I've left out of this is generally, we have a simultaneous problem where we are lost in space, and we also want to characterize our target, right? And so usually this problem is proposed as simultaneous localization and mapping, which I'm sure you're familiar with, and this is being able to locate your agent within a map and map out your environment that you're within. But here in SLAB, we've actually expanded this definition to be called simultaneous navigation and characterization. And so this is a superset of SLAM where it includes characterization of the environment, a target, even other agents within a swarm if you're in a swarm. So things like solar radiation pressure coefficients, your spherical harmonic coefficients for gravity or shape. It can include rotational motion, basically anything you want. So it's an expansion of these very traditional problem that we have in robotics and navigation and things like that. And what are the main objectives of the Autonomous Nanosatellite Swarming Project? Well, we want to develop a mission architecture that can autonomously perform SNAC, simultaneous navigation and characterization. And we want to characterize the rotational motion, gravity field, global shape, all of these characteristics autonomously in a manner that's safe, is computation efficient, robust to any sort of dynamics modeling, whether you're doing relative motion or you have global motion in the case of an asteroid. And we want to do all of this with low swap C avionics, so low size, weight, power, cost. We want to do this in a very resource constrained environment because we want this to be something that you can send up and use in any sort of environment and say, hey, I want to figure out what's going on here in effectively the cheapest way, the fastest way that you can possibly do it to get that information into your hands as quickly as possible. Okay, so what does this mission actually look like? Well, it will generally be deconstructed into 3 different phases. The first one will be a observation phase. In the case of an asteroid, it will be something like a high altitude survey orbit or a flyby, where you might be communicating with ground in the loop in order to get these very rough state estimates and things like that and say, hey, I need to just vaguely know the rotational motion. I need to know if this is a tumbling spacecraft. Is it 3 meters across? Is it 20 meters across? And then phase 2 is when we go into actual autonomous state estimation and autonomous characterization, that SNAP, where in this case that I'm showing you right here, where we're navigating about Eros, we have 3 spacecraft, and they have their low swap-C avionics, which includes RF links or short-range cameras, and they're navigating using landmarks. And this is where the autonomy comes in, and where I'm primarily going to focus the rest of this presentation. And the 3rd phase would be completing other science objectives, doing maneuvers, things like that. If you want to go into rendezvous and docking, that would happen in phase 3. Okay, so there is an overview of the pipeline here, and this starts generally with, sensors. And in this case, we have like an RF link and optical tracking where we're getting images of whatever our target is. And then those go into optical landmark tracking and stereo vision. So LiDAR is primarily a high swap-C sensor. You need a lot of power draw in order to do it. And you also have some pretty stringent range requirements in order to use LiDAR. So for this, we're doing purely optical landmark tracking, and we're using stereo vision to kickstart the initialization of any sort of state estimates. And then so this goes into state estimation with the UKF. And so these can go into global shape reconstruction, and this performs a loop of improving that global state estimation, improving those characteristics that we're estimating, improving the state estimation like that. And then this goes into guidance, which you can use any form of guidance. What we were using before is a neural net approach. It's really interesting. You can look into Tommaso's work if you're interested. And then after that becomes control and actuators for actually maintaining your system.
Yeah, question for you on the sense, maybe you're going to get into this. What actual information you're actually sharing? You're sharing the images from each spacecraft with each other, or?
So I'll deep dive into the optical landmark tracking and stereo vision and the state estimation, and I will go over what is actually shared in between them. But it's primarily the images are not shared between all the spacecraft. It is only the landmark positions of Earth. Yeah, so because images are expensive to, Okay, so the flagship case that I'm going to be showing you is an asteroid mission, asteroid rendezvous mission, and this is because this is actually one of the hardest cases we could do. They have their own gravity, right? So we need to be estimating those gravity coefficients along the way. There's very little prior information available. We can look at star fields for navigation, but generally you only have a rough shape and motion of the asteroid. It'll be like a blob and say, oh, maybe it's rotating about this fast. And what is unavailable is something like GPS. And very fast Earth relay is not possible. Even if you're a near Earth asteroid, you're generally talking minutes, hours, maybe even days of communication delays. So, and right now, the state of the art for these asteroid rendezvous missions, such as Hayabusa 2 or OSIRIS-REx, these are extremely expensive. They're monolithic spacecraft, and the data they get is incredible. It's amazing. However, they depend on these high swap-C avionics, such as LiDAR. They'll generally have multi-camera sensor suites. Some of them, like Hayabusa, even have deployed markers that they use for navigation. And these are highly dependent on human oversight and extremely computationally expensive algorithms, such as stereophotoclinometry. They use human oversight for state estimation, which obviously we're trying to move away from. We want things to be autonomous, and they obviously have budgets, on the tens of billions of dollars. Okay, so let's get into each of the aspects of these. So generally what happens is you'll get in this sensor suite of an image from each spacecraft. In this case, it's 3 spacecraft that look like up in the top left corner. And I'll go in and I'll perform key point detection in order to determine, what landmarks have I seen before? Are they craters, are they boulders? It doesn't really matter what the key points are. We just need to be able to consistently detect them and track them over time. In this instance, these are SIFT features descriptors. And then there are 2 things that happen simultaneously. One, I do sequential tracking. So have I seen this landmark before? Can I match it to something that's already in my database of landmarks? And this is actually what goes into the filter is pixel measurements of landmarks that I've registered and have tracked before and I'm consistently tracking. That's the measurement that goes into the UKF. However, you're starting from nothing. Right? When we go out to this asteroid, we have no shape model. We have no landmark gate arrays. So what needs to happen is we need to initialize every single one of these landmarks into a 3D database, like you can see up in the top right. And so the way we do that is of these images that are taken simultaneously by the spacecraft, we perform matching between them of those key point features, and we perform stereo vision between the 3 images or 4 images, however many spacecraft are in your swarm. And those clock synchronization estimates are being estimated within the filter. So we're accounting for any sort of clock synchronization error during stereo vision through those state estimates. And that is able to get us a 3D position of every single landmark in order to initialize those states for the UKF to track them and modify those state estimates over time. Okay.
That would be relative to.
The landmarks are tracked in an asteroid-centered asteroid fixed frame. So we have like a target fixed frame that we keep the landmarks in.
Gotcha.
Mm-hmm.
So the first few landmarks or something that you identify, you'll use that to anchor your frame.
Yeah. So generally, we're assuming that in the phase one, like observation, you may establish a frame of motion with a rough rotational estimate. And with asteroids, they'll pick a very large landmark, like on Eros, there's this large crater here. The x-axis goes straight through that. So they pick an arbitrary frame, and then you kind of anchor it that way. So yeah, so you would still anchor with the first few that are in there if you were to really start this from scratch.
Yeah.
Yeah.
Yeah. If you capture rotation,
yeah,
the center it's probably easy.
Yeah. Okay, so I keep talking about the state estimation filter that is updated with the landmark state estimates and everything. But what is actually going into it? Well, first of all, we're using an unscented Kalman filter, and this is much more computationally efficient than the traditional extended Kalman filter. We're using measurement underweighting, and this leads to a lot more robustness in the system, and we're using adaptive state noise compensation. So this is a method developed by my co-author Nathan Stacy in order to do this. And again, we're assessing all these clock offsets to account for the multiple agents that are being estimated within the system. And on the right here, we have all of our definitions that are being estimated within the state of the UKF, right? So we have the Cartesian states of all of the spacecraft, and this is within an inertial frame centered about the asteroid center of mass. We have the radiation pressure coefficients of all the spacecraft, the clock offsets and drifts with respect to a chief spacecraft. And then we have the asteroid characteristics, which includes the gravitational coefficients, rotational parameters, and included in that are the landmark position estimates. So you're maintaining a 3D point cloud of all of these stereo vision estimated points that you're tracking over time. And these state estimates are also used to estimate, like, are we looking at this same landmark again and again? But there's also a paper that we've produced on this, and it's soon to be a journal paper. And there's a lot more information that goes in behind this.
You're not labeling your landmarks, though, are you?
Not generally. There's a process where they get eliminated over time if we don't track them. It is a long enough period to get eliminated. Okay. So, and then the other aspect of this is global shape reconstruction. And we actually do this with spherical harmonic coefficients. And so we fit a body to our entire point cloud of 3D points. And this is done via least squares. And so you can fit all the global shape reconstruction coefficients to all of these point clouds. And we know that this is what an asteroid should look like. However, if you get too many points in some areas, but not enough in others, this generally leads to overfitting, which is not great. But we know that this is what asteroids are actually supposed to look like. And so what Nathan developed was actually a regularization factor added to this spherical harmonic coefficient that leads to the spherical harmonic shape models actually fitting what you expect them to be from an asteroid. Okay, so let's take a look what this actually looks like in practice. And so with this, we have 3 spacecraft that are orbiting in a string of pearls formation, separating the along track direction. They're orbiting at 45 kilometers about asteroid Eros. So Eros has an 8-kilometer radius average for your reference. And this is kind of the result of that system. And so you can see up here is the navigation filter, position estimates and velocity estimates being refined over time. And in the bottom left over here, you see the landmark point clouds are all the 3D, are the green points, and the spherical harmonic shape is being fit to them over time as those landmarks come in. And also the gravity coefficients that are being refined over time. Yeah.
So I hadn't realized that the orbital period is smaller than the rotational period of the asteroid itself.
Mm-hmm.
I personally haven't looked at what the orbital mechanics of what that looks like, where your gravitational coefficients are a function of time.
Yeah. Yeah, it's a really interesting case, and it changes obviously from asteroid to asteroid. Like Ryugu is a very small, it's like not even a kilometer in radius. So you would get a very different result from that than you would from Eros, which is a very large asteroid. Yeah.
And have you, like from an observability standpoint, because like you said, you're not only trying to estimate the position of the spacecraft, but also the gravitational coefficients. Yeah.
Mm-hmm.
How have you established the observability of that?
So we're pretty, with Prisma, for example, I started, it's typically done in Carrier phase differential GNSS, to estimate tens and tens of state parameters in a common filter, and I've never seen problems of observability as long as you have the measurements you need. Here we have not done a rigorous observability analysis. However, from first principles, you have a triangulation with cameras tracking common features, and you have the crosslinks between the satellites. So the orbital motion is geometrically observable, and the gravitational field over time is observable because it's driving the motion of the satellite over time. So I'm not afraid about lack of observability as long as you have measures. Now the question is what happens over long data gaps, but I could imagine that we could reinitialize this whole navigation architecture and being able to recover things properly.
We do that when we run into dark, because lighting is obviously an issue when you're only using the cameras, right?
Yeah.
So when we run into blackout periods, we just reinitialize the filter, and it's able to pick back up again after.
So
those
from
periods.
geometry, it is observable.
Okay.
So,
Okay. Great. When I think when you think about a particular effect on the motion of the spacecraft,
isolate.
how do you isolate it, right? Because, for instance, it's a good example. I think an asteroid over here. I don't know the order of effect that the magnitude of effect that would have. For instance, if you think about solar radiation pressure, right, versus the third party effect versus the rotation of the asteroid itself. Potentially, they could all be of the same order. Like these various effects can cause the same type of perturbation to the spacecraft, right? That's when you start thinking about problems related to observability.
Mm-hmm.
From the grasp of it, it looks like a very dynamic event.
Mm-hmm.
Yeah, theoretically, it's possible that there could be some ambiguity. However, it's very difficult to encounter. The shape is not driving the motion of the satellite. On the dynamic side, regarding
the shape is not driving the motion.
The shape is rigid, it's a rigid body.
Oh, I see.
Okay, so the motion of the satellite is only a function of the gravitational field and solar radiation pressure and third body perturbations. And there, adaptive process noise, so you can capture those effects that you are not modeling in the common filter as empirical acceleration. So you can absorb these effects as an extra acceleration acting, fictitious, acting on your satellite. So
okay, so those perturbations
if you want this ambiguity, obviously you could see offset in the estimation of some parameters that could be hidden.
Yeah.
Biasing maybe one parameter more than the other, but overall, so the system is observed.
Is there any interaction from your shape recovery back to your landmark matching? Because you can see they don't exactly lay on top, but you're not.
Yeah. So as of right now, there's no talking in between the spherical harmonic and the 3D modeling. Yeah. So.
I mean, it gets there in the end, but you can see, does it good or bad that it's not agreeing at time periods.
But we are in in that direction, because we have developed algorithms for ray tracing to a spherical harmonic model, so we can use the spherical harmonic model as a surrogate, 3D model for to aid identification and tracking, but that's for future potential future research.
Yeah, because ray tracing through because ray tracing through like a polygon model like this is actually quite expensive. But ray tracing through spherical harmonic is instant because it's simply a math calculation. Whereas like the ray tracing through a polygon model is, you have to calculate all the vertices and all the faces and things like that. So yeah.
And then there are interesting aspects regarding the exploitation of knowledge of shape and gravity and putting them together.
For that,
distribution, you get the inertial tensor, you can compare with the order and degree of the gravity field, and then make the exact consistency of what you are doing is correct. So it's quite beautiful, and it's giving me interest of entering into the geophysics because you start getting after shape and gravity, the constituent, and you can get the density map of the asteroid, and then start thinking beyond and the potential exploitation of the asteroid for resources and all these things by just orbiting around it. You don't need to land on it, and you can do a survey across imagining the asteroid belt and doing this, swarming around multiple asteroids and build a database and identify those asteroids that are of interest to us, so forth. Very, very interesting things.
Okay.
Let's take it.
Okay, just a quick note about the stereo vision results. What you can see here is obviously this is in the camera frame. So the bore sight direction, we have a 1 sigma standard deviation of about 147 meters, which on the scale of things, I'm 45 kilometers from my target surface. So that's a very good result. And it's highest in the bore sight direction. In the axis directions, we have 72 meters, which is very good. It's just farthest in the bore sight because obviously that's the measurement we're trying to recover is the depth. We know that X and Y direction quite well already from the pixel measurements.
Talking about a priori information, and you can answer this later. How much do you need to know about the asteroid to enter into an orbit around the asteroid?
So we basically need to know the rotation. That's the most that we need to know is the rotation rate. That was the hardest thing.
Yeah, you need to know mu.
Right, mu. But those are things that actually can be estimated with a telescope. Depending on the asteroid as well. So you can be pretty far to get this data. You could even do Earth observations in order to get it prior. And then the state estimate, we initialized the system with the same state estimates the Near Shoemaker mission from 20 years ago used. And it was like 200 meters of initial state estimate error, which today would probably be much better starting out. But you start with very little information in order to get these results.
So the data that you have to enter an orbit around an asteroid is the data that you use as a priority here.
Yeah.
So actually less, because we don't use knowledge from the shape.
Right. There's no shape knowledge used prior. So yeah. Okay. We'll just skip this. I think you've seen it. Okay, so the next thing to do is to actually generalize this target. So I've talked a lot about how we would do this for a small celestial body, right? But the end all be all goal is to kind of have an amorphous target that we're looking at, whether it's a spacecraft, whether it's a rocket stage, whether it's orbital debris or something like that. And kind of the next thing to do is to take a look at a man-made spacecraft and can we apply these same situations to it? And this is where my research is going in this. What you have to do is look at all the domain differences between this, because there's a lot going on when it comes to looking at an asteroid versus looking at a spacecraft. And the first one is obviously like the key points that you're using is SIFT works so well on asteroids, but when it comes to something like the Tango spacecraft, it doesn't work and you need to use orb instead. And you need to characterize how am I going to go in and change all these different things. And tracking as well. So SIFT, again, works really well for these asteroid situations, but it barely works at all for the spacecraft. You basically can't match them. And then obviously the structure recovery, and this is something that I've been looking into a lot more with my research, is there's actually a lot that goes on with the relative position of all of the agents involved. If you're having synthetic aperture stereo vision that you're using, or structure for motion, there's a lot that goes into, how close are your spacecraft, how close are your observers, how close are they to the target itself, because that determines, how fine-tuned you can get those pixel measurements, and how much the error influences your end results. And then also the spin state, right? Like I talked about how we really need that rotational motion of the asteroid. Well, a spacecraft is probably tumbling, and that's going to be way more difficult than a single axis spin. And then the swarm geometry and dynamics, right? So I have my 3 spacecraft string of pearls for the asteroid, but that's probably not what we're going to be doing if we're looking at a spacecraft that, we're going to go perform maintenance on or something like that. It can be 2 observers, 4 observers. How many observers do you need in order to get this best information? And also clock synchronization. This is a huge issue, especially when it comes to images, because if my images are misaligned, that 3D data I'm getting out of it is going to be useless. And then state estimate uncertainty. This time, if you're looking at a spacecraft in LEO, we have GPS, which is great, and that can greatly improve those measurements you get out of something like stereo vision or triangulation. And it's completely different than using the range measurements you'd be using from the Deep Space Network. And then finally, sensor noise. A lot of people ignore the sensor noise that is coming in, whether that's camera image skew, camera image noise, things like that. What is the actual jitter that you're getting on the star tracker for those attitude estimates? Because in order for me to recover these 3D states, I need to know the attitude quite well in order to do that. So how disruptive is the attitude to actually the measurements that are coming in? So the end all be all goal is to be able to apply ants and SNAC and all these things to an asteroid and have it also work on a spacecraft in the end. So we have a system that can go out and characterize whatever target you're looking at, depending on whatever swarm state you have, whether it's 1 spacecraft, whether it's 6 spacecraft, and maybe your camera is good, or maybe it's really great. We want to know, how does the system adapt, and are we able to apply it to all these different situations? So just in summary here, we want to be able to apply this autonomous nanosatellite swarming with all of these low-cost sensors and data and applications to as many different target characterization domains as we can, whether it's a comet, whether it's an asteroid, whether it's orbital debris or a non-cooperative spacecraft. We want to be able to do it. And we're doing this in a domain that is expanding upon the traditional SLAM format and do something that incorporates navigation alongside characterization. Okay. All right.